In this lecture, we look at the magnetic force on a wire. A current in a wire consists of moving charges. Moving charges in a magnetic field feel a force, so a wire with a current feels a force if it is in a magnetic field. So here we have a magnetic field that's pointing out of the page towards you. We put this red wire into the field, and we get a current. Imagine a small length of the wire, delta x. It has a small amount of charge, delta q, in it at some point in time. The magnetic force on that small charge is then given by the magnetic force law for a charge, for a moving charge. So delta F is equal to delta Q times the velocity of that charge crossed into the B field. The force then, we can rewrite this a little bit. We write the velocity as delta x over delta t, where delta x points along the direction of the current. We rewrite that again so that we pull out the delta t, so we have delta q over delta t, and the cross product of delta x and b. Well, delta q over delta t is the current. So this small part of the force is equal to the cross product of delta x and the B field times the current. And the direction of that, if you put, using the right hand rule, you put your fingers in the direction of the current, curl them into the direction of the B field, pointing out, and your thumb then points in the direction of the force, or to go down and to the right. Of course, the wire bends through this field, so another part of the wire would feel a different force, so the force on the whole wire is rather complicated. There is a simple case of a long straight wire of length L in a magnetic field. There, the total force on a long wire is just the current times a vector L crossed into the magnetic field, where the magnitude of L is the length of the wire, and it points along in the direction of the current. Let's take a look at an example of the magnetic force on a long wire. Here we have current flowing upward on the page and the B field pointing straight out of the page toward you. If you put your forefinger along the current direction and curl the other three fingers upward in the direction of the B field, then your thumb points in the direction of the force, so that this wire feels a force that tries to move it over to the right. If we switch the direction of the current, so now that it goes downward, we now put our hand there, curl our fingers up, and our thumb now points to the left, so the wire wants to move over to the left. If we switch direction of the B field, now when we put our fingers pointing down, our forefinger is pointing down and our three fingers are pointing into the page so you don't see them, and your thumb points off to the right, so the forces now goes off to that direction, so the wire would like to move over that way. Let's look at a problem. For a magic trick, you'd like to levitate a wire by passing a current through it in a magnetic field. You choose to run the current from right to left. The force of gravity is down, so the magnetic force should be up. Which direction must the magnetic field be in? Well, we put our trusty right hand into the picture, and we put our forefinger pointing in the direction of the current, I. We need the force to be up, so we put our thumb upward. That leaves the tips of our other three fingers pointing directly toward you. So it's towards you out of the page is where the B field has to be. So now we'll put the B field in. So we have the direction taken care of. The mass of the wire is 1/10 of a kilogram, and its length is 1 meter. If we put a current of 1 amp through the wire, what is the strength of the magnetic field we need to make it levitate? Well, we use the force on the wire is equal to the current times L cross B. L and B are perpendicular to each other, so the magnitude of the force on the wire is just the current times L times B. And that's equal to mg, the force of gravity. Solving for B, we have that is equal to mg divided by IL. And plugging in the values, we have for the mass 1/10 of a kilogram times the acceleration due to the gravity, 9.8 meters per second squared, divided by the current, 1 amp, divided by the length of the wire, 1 meter, and we get a value for the B field that is equal to 0.98 Tesla.